All right, I'm going to be just taking care of making sure that people are all accepted, and just let you, I guess, introduce yourself from now. The floor is yours.
Do we start now?
Sorry?
Do we start now?
Yeah, we can start now, I guess. Yeah, I'll just keep accepting people, but yeah, I think we can start with intros and stuff like that.
Let me share my window. Can you guys see it?
Yep, all good.
Okay, cool. So, okay. So hi everyone, thanks for coming. Today's topic is a guide to symbolic execution. It's going to be a high-level introduction to symbolic execution. It's a type of method of program analysis. Hopefully, by the end of this lecture, you'll learn what it is, and also about formal verification, and start building your own tools about symbolic execution. You can interrupt me by raising your hand, but I'm not sure if I can hear. But you can also keep your questions till the end. There's a Q&A section. So, quick self-intro. My name is Chi. I was a security researcher at Fuzzland, a security company now acquired by Solayer Labs, and we're building a new L1 now. So last year at Fuzzland, we were building on-chain automatic solutions. Mapbots were one of our tech stack, and I was mainly focusing on taint analysis, using symbolic execution and advanced fuzzing techniques. We made quite some profit on chain last year, and since the team is now focusing more on the development, I think it's good to share some of our past experiences on MEV and symbolic execution and fuzzing stuff. So let's have a recap on fuzzing. So I assume you have taken the fuzzing course already. Fuzzing can be split into the following stages. First, you generate a random input, then execute the program you're interested in with this input. You then observe and analyze the execution, collecting interesting information, for example, the execution path or coverage. If certain conditions are met, including invariant violation or bugs, which we exit. Otherwise, we just repeat. And let's look at the sample program for reference. So in this function on the left, the buggy state will be reached if the first byte of the instruction data is less than hex 80. Otherwise, it would be just the not bug branch. So how a fuzzer will find this bug is that it will first generate a random slice of U8 and then execute this function, pray for the first byte of the instruction data is less than 80. And if it's not, we just repeat. And we can calculate the probability of finding this bug. So each run we have 50% of chance generating the buggy input. If we run it 100 times, the probability is virtually 100%, assuming the fuzzer will only mutate the instruction data, not the accounts there, and also the length is always greater than 0. And we can change if we change it was a small less than sign. If we change the less than sign to a equal sign, we can also calculate the probability now. It's going to be, for each run, it's going to be 0.39%. And we run it 100 times. The probability of finding this bug successfully using a fuzzer is around 67.6%. I know 100 runs is way less than an actual fuzzer. Usually a real fuzzer will do hundreds of thousands of times. But here it's just for reference. And let's further complicate the program. So now it checks 2 bytes. If the first byte is hex 80 and the second byte is hex 81, we reach the bug state. And now the probability is way lower. It's for each run 0.00152%. And if we run it for 100K times, the probability of successfully finding this bug is only 21.7%, which is not good, because apparently as a human being, you can read this code and immediately tell how we can reach this buggy branch, right? And our goal is to like let the fuzzer or let the program to smartly like find this branch. Yeah, that's the main idea of like symbolic execution.
We have a question from Amit. He's asking, how did you come up with 67.6%? Is it binomial distribution?
Yeah. So for each run, like you have 99.61% of not finding the buggy state successfully, and if you like take the power to 100, that's the number there. I will continue. Okay, so let's look at the programming another like graph here. This is a so-called like control flow graph of the previous code snippet. It's often used in program analysis, and it's pretty straightforward. Like we now have a few branches and conditions in the graph format, and I will show you how a symbolic execution engine works here. So we, instead of like executing the program concretely, we execute it symbolically. What that means is that instead of like using a concrete actual numerical value, we use a symbolic value. For example, in the first bracket square here, we think that we assume the first byte of the instruction data is a placeholder. A concrete value is like real numbers, and symbolic value is just a placeholder. When we meet the first separation of branches, this yes or no, and we will, let's just assume we actually take like both branches, but let's just focus on the right branch first. If we take the no branch, we will reach a final state of this square here, and we will also add a constraint to this branch, that the first instruction data of first byte of the instruction data is not equal to hex 80. So if it's not equal to hex 80, we will enter this rightmost branch. And similarly, if we go yes, then no, we will reach the middle state. And the constraint here is the first byte of instruction data is hex 80, and the second byte is not hex 81. And also for the left branch again, if the first branch is hex 80 and the second branch is hex 81, we will reach this buggy state. But like, although I'm referring to, like, I keep saying buggy branch, but it's really just a special branch. So now we will introduce something called a SMT solver. You don't really need to understand how a SMT solver like works internally, or the mathematics behind it. I'll just tell you like how what does it do. So basically, it gives particular solution of a Boolean expression. For example, if we have x greater than 0 is true, the solver will tell you x equal to 1 will be one solution of this Boolean expression. And also it tells if an expression has a solution or not. For example, if for this Boolean expression, if x equal to it must equal to 1, meanwhile it must equal to 2. Apparently this is not possible, right? So the SMT solver will tell you this is a unset, stands for like unsatisfactory. And that's the two main functionalities of SMT solver. And there are two famous solvers. One is Z3. This is the most used one, and also CBC. So with this SMT solver and our previously collected branches and constraints, we can ask the solver to give solutions that the conditions can be met. You can see the difference, like for this, like from different from fuzzer. So it will give exactly 3 solutions to the 3 branches, but for a fuzzer, it might give like hundreds of thousands input, may or may not cover all the branches here. So now we can answer a very fundamental question. So what can a symbolic execution engine do? Like basically, it proves a branch can be or can never be reached. This has two applications. One is formal verification. We can prove that a buggy state of a program can be or can never be reached. For example, for some like token program, we expect the total circulating supply never exceeds the total supply, right? So symbolic execution is one type of formal verification. There are some other types of formal verification. For example, you can do some like manual proof, like you did in your college classes, using induction or other things. But like symbolic execution is more general, and also it's more like low effort. Satora Prover is, I think, is the only like application I saw on Solana to do this formal verification. Yeah, you can try it out. I haven't tried it out, but I think it's still in experimental process. But yeah, play around with it. Another application is automatic program analysis, and this was what I was doing like last year at Fuzzland. So the main idea is that we analyze every newly deployed contract using fuzzing and taint analysis. And taint analysis, like we use a symbolic execution for that. And I have a talk at DeFi Security Summit. There's a link here. I will post this the links to this slide later to the chat. And it describes how we use the fuzzing and also like some sort of like symbolic execution doing on-chain math bots. So now let's talk about like some component we need to build a tool based on symbolic execution for any purpose. Yeah. So first you need an execution engine, apparently, like we did in the manual walkthrough in the CFG part. We need to execute the program, right? And you need a customized SVM environment for that. And I think that Anza, in their Agave code base, SVM is now separated, and you can use that API easily to build your own SVM. And the main thing you need to customize is that you need to do instrumentation. Instrumentation is that it's a concept like observing the execution state. There are two types of instrumentation. One is white box, and another one is like black box. For white box, it means that you have the source code of your program. It is what Satora does, Satora Prover. Basically, you define in your program, in your source code, what is a bug and what is the invariant, what is the condition that can never be broken. Like I mentioned before, like in the token program, the total supply, right? Like anyone's balance cannot exceed the total supply. That's one example. And when you define, after like you defining this invariance and the rules and like instrumentation stuff, the Satora Prover or your own tool should like look for the branches that reaches the target state. For example, if we somehow reach some target state of a token program that the balance is exceeding the total supply, hopefully Z3 or other SMT solvers will say that it's impossible we can reach there. Then your token program is fine. It's provably correct. But if the solver solves for some input that this bucket state can be reached, then we have found a bug in your source code. And the other one is like black box instrumentation. This means like we do not have the source code of a program, and it is more used for on-chain analysis. We did this on EVM. We used REVM and also like customized execution engine. And we focus more on the bytecode level. So basically, when like for every bytecode, you observe the state of your virtual machine. For example, you need to know whether we reached a branch or not, whether we are doing some arithmetic operations. How do you manipulate the placeholders, the symbolic values there? And finally, how do you define what is a bug? And this is like, kind of heuristic for the, if you have the source, you know what can be broken, what cannot be broken, right? But for black box ones, it needs your like imagination or like your definition to know what is a bug, what is not a bug. Like for our MVB bots, we consider like our transfer is a bug. For example, if some program can let you arbitrary transfer token from anyone, it's going to be a bug. And we will try to exploit that. Also, like arbitrary mint, that's also a type of bug. Access control, I think this is like this is one major issue on Solana, because like many people use Anchor to write their program, right? And for Anchor, the one of the biggest bug is like access control. If you check the signer, if you check the authority, something like that. There are tons of other constraints you can think of, you can add there. And now I want to talk about like challenges and trade-offs of like symbolic execution. And like this is like the reasons why people did not adopt symbolic execution so widely. So the first one and the biggest one is path explosion. What this means is that like we said before, when you reach the branch, like you have two states. And if you are in the, say, for loop, every for is like, it's gonna split another branch. So the state, like the growth rate of the state is exponential. And if you have like n iterations, you will have 2 to the n states, and it will like the path will explode immediately. And also like for serialization, this is common in Solana development, right? You use like bin code to serialize or deserialize stuff, and the code there is code inside bin code is quite complicated, and there are tons of like loops, and you don't want to like tell the solver spend time to calculate or to solve how the argument will be. And the solution to that, well, it's not technically a like perfect solution, but it's just a trade-off. Is that you do branch pruning, and you add external heuristics. For example, you can add the definition of the instruction, the IDL there, so that you will know that what part of the instruction can be, treated as symbolic value, or sometimes you can just treat them as concrete value. For example, in Solana, you can use the IDL for discriminator, right? You don't need the solver to help you to solve for the discriminator, because that's just waste of time, and you only want the solver to truly like solve for the key part that will affect the execution flow. And the second point is the infeasibility of some complex operations. One example is hash function. Again, like you cannot reverse or solve for hash function. You know some hash, and you cannot use that hash to solve for the original. Even SMT solver cannot do that. And if you try to let an SMT solver to do hash function, it will just stuck there and run out of resources. And for these types of things, you need customized handling. And also, like, there are other things like syscalls in Solana. You might also want to do a customized handling for that. And it's not really a solution, but it's more of a target specific thing. And if you want to build on Solana for the tooling, you might want to handle that. And the last thing is speed. So for complex constraints, like solving for a solution can be timely, especially like there are hundreds or thousands of like equal signs or Boolean expressions there. And sometimes like for MEV operations, it's not, I haven't seen it on Solana yet, but back on EVM, like we need like time is everything. Sometimes a newly deployed vulnerable contract, like when as soon as it's deployed on the chain, other MBB bots using their techniques are trying to exploit or try to run the transaction, exploit the contract, or try to make profit from it. And sometimes it can be like time is everything. And as although that symbolic execution is very precise, like solving can take time. So we need to like find some other solutions for that. And one solution is Concolic execution. Concolic is the combination of concrete and symbolic. It's basically we I actually like mentioned it before, like you treat some values as concrete values and you treat some values as symbolic values. You only focus on the most important part of the symbolic values. And that will like, it's more like a fuzzing plus symbolic execution. But on the other hand, since there, you ignore some cases, you might not, you cannot, it cannot be called a formal verification. Like you don't have 100% of coverage. You may have 99.9% of coverage using Concolic execution, but that's already like good enough for MVB bot. And yeah, here are some tips about like for those who are like you're interested after this lecture. So building a symbolic execution engine tooling is easier than you expected when you get your hands dirty. So basically all the knowledge you need, it's already covered in this lecture, and all you need is to write code. So the engineering effort is way bigger than the knowledge needed. And also, like, I mentioned the challenges we have met, and it's just a workaround when you see the specific challenges. And also, like, the final tip is that symbolic execution on Solana, I think it's way underexplored. And I have not seen MEV bot like competing very severely on Solana on chain. But on the EVM side, yeah, bots are evolving very fast, and you can refer to my talk on DevCon last year after this. And that's it for the lecture itself, and I am open to questions. Oh,
hey Chi, yeah, thank you so much. Oh, is there a question from someone right now?
yes, in the chat. It's DevCon. Yeah, it's last year in Thailand.
Got it. Yeah, DevCon. Let's go. Yeah, I wonder if I'm just thinking if there's any ways of sharing any live demo of how symbolic execution works, maybe on the EVM contract, or maybe just you have some demo ready. If not, no worries. Maybe you can just link to some talk that you've done before.
Oh yeah, let me first share this doc. I don't really have a demo live with me. Let me first send the link to this slide to the chat. And do you guys feel that this is like a bit too high level?
Yeah, I mean, depends on the level of people here, but I guess a lot of people here played with symbolic execution tools before on EVM side, at least. I think maybe half of them, at least from what I know. So yeah, that would be cool to see something. But again, if you have just maybe some good links to link people, I'll just prepare this reading material right after this lecture. We'll include this talk and maybe some more advanced topics, some more advanced demos and stuff like that.
Yeah, sure. I will update in the Notion page later. And I saw a question from chat. Can I talk about more like branch pruning. Okay, so basically, what branch pruning is aiming is to eliminate the unnecessary calculations for the SMT solver. Let me actually share. Let's do this. Okay. So let's see. Let's have a look like how a for loop look like. So this is a Rust code. Okay, it's compiling now. So this is a for loop. Okay, let's actually not use Rust. Let's see. On the right side, we have the the compiled x86 instruction, and this is a for loop, right? You see it as a loop, but indeed it's just there's a compare let's look at it like this step by step. So you first store something on the stack here, the EDI, which is actually okay. So look at this instruction here is JLE, which is jump less than. So it's comparing this value here stored on the stack with 9, which is here, right? It's comparing to 10. So here is 9. It's because it's less than less or equal to. And for a loop like this, the compiler will compile it to the right side, and it's gonna be if you look at this control flow graph, it's gonna be like something. Let me draw it. So this is this is like kind of it's gonna be like this, and we have like 10 of that. So we have like 6 branches, right? So a for loop will this is a for loop of 7, and you have 6 branches, and we don't. This is like the path explosion. Every time you split a path, and if we inside here, if we instead of like just do increment, we have some other logics, the state will explode exponentially very fast, and the resources will be used up. And that's why we need branch pruning. And the method of like branch pruning, but it's very challenge specific. For example, for here, we don't really need to. If this is for example, if we have a program like this, if num is 99, say this is a bug, and when we're using symbolic execution, for this part, we don't really need to care about what branches should be added to the entire engine, because we know that this part is not relevant to the bug itself. So this is like we can prune this, but this is a very simple example I'm raising here. You might need to design your own branch pruning techniques there. I hope this makes sense. Is it okay to not fully understand? Yeah, I think so. So all the challenges only like pops up when you're starting to build tooling for that. But what specifically did you not understand?
Okay. I think I would just probably look over everything again from the beginning. I have opened the slides that you opened up, and then you shared rather. I'll thoroughly look into everything again. If it's possible, probably if we can get like a demo or something that we can, look through it as well eventually, that would really be amazing. Thank you, Kay.
Well, actually, I think I had an idea that I will be deploying a like puzzle contract on Solana someday later that can be solved like immediately with a simple symbolic execution engine. And I might post that on Twitter, and hopefully someone like maybe 2 weeks from now, maybe someone can I'll post it, and if we can like claim the prize, then congratulations. I think you're on the right path.
Yeah, that'll be fun. We would love to support the sort of CTF if you want to initiate something. Would love to collaborate between like Krakow community.
Yeah, I doubt there are
Yeah, should be fun.
no people like are doing this on Solana right now, and it's gonna be a good place to start. And as a MEV searcher, one thing I really took away from like the competition is that if you're one day ahead of any other MEV bot, you will be really rich. So since there are no competition on Solana right now, I really suggest you to try on that.
All right, that was a call to action. Thanks, Chi. Thanks a lot. Yeah, I think if you would have maybe some introductory materials on symbolic execution, I think your slides are more than enough to start with, but also some lectures, some videos that you liked before. If you can just drop some links, and I'll compile that into the Notion doc and share with everyone on the bootcamp. That'd be really cool.
Yeah. Yeah, and also I think later I'll send you one like small symbolic execution I did for Move. It's a tool I did for Move like for some CTF challenges, but it's also a good place to start because the code base is not that large, and basically it covers what I said in this lecture.
Cool. Also, a quick announcement. We'll do the more official announcement probably next week, or I think later this week. But yeah, she's joining Erectov as a security mentor. So yeah, feel free to maybe just ask some questions if you have any on symbolic execution or similar topics. Yeah, she will be on our Slack from time to time. So yeah.
Okay.
Thank you so much for joining. Yeah, that's going to be fun.
Can you share in brief how we can use symbolic execution in MEV? As symbolic execution takes longer time. Okay, yeah. So let's well, for MEV here, I am referring to like more general MEV. It's not arbitrary or liquidation alone, because like these are you can do it by like using rule-based ones. For MEV, I'm talking about is that, for example, one scenario we did was that we tried to fund run like hackers transactions. So on EVM, there are hackers like if you want to hack some contract, usually they use a like support contract or helper contract to initialize all the calls there. But sometimes if you simply write a function called trigger with no parameters there, basically as soon as your contract gets deployed on EVM, people will know there's a function, and it's called trigger with no parameters, and they can just simulate what happens if we hit this trigger. And sometimes like people can like hackers got fun run by this stupid method, and then hackers evolved. They added parameters into their their trigger function. For example, they changed their function to trigger plus some address, which is the victim. And this is where like symbolic execution like kicks in. You can or maybe address is not a good example. Maybe let's say amount. If how many amount do you want to say hack from the victim? And if the amount is equal to some specific value, this hack will succeed. And if it's not, the hack will fail. And this is where like symbolic execution can kick in. We can solve for a value that the transaction will succeed. Succeed means that you can transfer money from some victim, or like increase your balance from nowhere. And that's how we used in MEV. It's not arbitrage MEV. Yes, arbitrage, like you usually use like algorithm to calculate the graph stuff, and that's the MEV I was talking about. And symbolic execution, sometimes like this is the only solution to these types of challenges. Like there's no rule or pattern matching method that can allow you to fund run these types of transactions. And this is like also like included in my slides where the in my talk previously. Yes, we had one fuzzer which works on symbolic. Yeah, it's called ETFuzz, and we haven't like updated it for some time, and we're not planning to do one for Solana right now. And the reason for that is that Solana, we think that it's like for these types of tools, like if you want to target to some projects, say if you want to use fuzzing or symbolic execution in one audit, you probably will spend a lot of time searching for nothing. But if you like write a tool and scan for all contracts on chain, you might end up like finding a lot of vulnerable contracts there. It's open source for contributions. No, we don't have a Solana fuzzer now. This is the EVM one. Cool.
Oh, one more question here.
Okay, cool. How would you know what parameters to pass in the function, like the call data? Yes. So again, this is like included in my previous talk, but I mentioned briefly here. So basically, you have the signatures. So you know the types of the parameters, and for example, if you know some parameter, there's only one parameter called amount, and that's a U256, and you will like I wrote a taint analysis engine based on symbolic execution, that Z3 will know that this is a U256 to solve, and there's no for call data, for call data, if it's in bytes, then it's kind of complicated. We have some specific rules. For example, for call for bytes, we might assume that the byte is either be hashed or be another parameters that pass into other calls. So we will try our best to analyze that. Maybe it's an arbitrary call, right, in Solana, in EVM. So that's also like that type of vulnerability you might want to avoid, like if you call on someone else's behalf, right? Does that answer the question? How likely is that someone? Yeah, so the it really depends. Sometimes like fuzzers are faster. Sometimes the fuzzers cannot find anything. Like in the example in the slides, like if you for this code, if it's like this is a simplified version, but what if it is like some comparison to some address? So one address has like 32 bytes, yeah. And if you are comparing every byte of it, a fuzzer will never find it, but the symbolic execution will immediately find it because it's just a bunch of equal signs, and you can assume you can already like guess that it's gonna solve very fast, right? Because it's like even obvious to human eyes. Yep, that's my video. Yeah, this example like explains why sometimes like symbolic execution is better than fuzzer, why sometimes a fuzzer is better. That video is a shorter version. There's a identical topic I give on the DeFi Security Summit, which is in the link of in the slides. Here. This is the video. Yeah, this is a 20-minute video. Is your question answered, Ahmed? Cool.
Yeah, all right. I think all right, one more.
Well, actually, I haven't counted like how many contracts are like whether there are more contracts on Solana or Ethereum, because I feel like if you are trying to, I feel like Ethereum has more contracts because it does not allow you to call multiple contract easily unless you like use some helper functions like multi-call contracts. So if you want to call multiple contracts, you have to deploy a helper contract on the Ethereum. But on Solana, you have multiple instructions directly called. So I assume that there are less contracts on Solana. And also, so in early stage of like this computation, like fuzzer symbolic execution MVB bots computation, you don't really care about speed. Like you can scan all existing contracts there, as long as they're, looks like suspicious to you. For example, if it's just like hello world contract, you can do some like preliminary eliminations of those ones. If it doesn't change anything, if it doesn't have any PDA, does not have any fund assets there, you can just get them. But I assure you there are some like exploitable or vulnerable contracts there. And yeah, so I don't think there are like if we were to build some similar solution for Solana, like we did on Ethereum to fund run other transactions, I don't think it's gonna end up good. But I do think there are like existing vulnerable contracts on chain now, and I think it's kind of difficult to run SE for all programs. Yeah, you might need to want to filter some out. But yeah, I guess maybe my like puzzle will be the perfect target to for your symbolic execution engine. Okay, any more questions? Do you think ETFuzz is a good start to implementing it for Solana? Well, I don't recommend you use ETFuzz for like your personal tooling because it's more for a general purpose one. I like even for us, like when we're doing the MEV part, we rewrote a toolchain to do all the fuzzing stuff because of like speed. Etyfuzz it has a long start process, and also like it's aiming for lots of like general bugs there. If you look at the oracles we defined there, so study materials, let me think about it. So I don't know if there are existing study like or source code you can refer to, because this is as long as I know, like all the MEV computers we had, the code is worth millions of dollars, right? But since like ChatGPT are so strong now, and or AI in general are so strong now, I think you can just talk to them and give them your idea and let them to design a framework for you. And I think, yeah, I mentioned that I will drop my symbolic execution engine for Move. It's written in Python, but mainly like it encaptures all the concept I mentioned. You might, I think that's the best study material I can think of to start off and now. I will send it to Greg, and I'll post it on Twitter too.
Gee, I wonder, have you heard about Safe Harbor from Seal? Have you heard about this initiative?
Yes, I know. Like we're a member of it.
Nice. So yeah, I think if one of you managed to find a bug and the protocol is not very cooperative, I think they have this whole agreement behind the Seal. Seal is one of the biggest initiatives in, I think in Ethereum space. They're also probably supporting other ecosystems now, but they have this agreement, which is called, I think, Safe Harbor. I need to double check that, but you can, I think protocols are signing this agreement in order to secure like white hats legal ground, sort of, to make them, kind of not get into the gray area. Yeah,
that's a good resource. And for those like actually for those big protocols, like they have like millions of TVLs, it's unlikely to find a bug using this technique. Usually our amount is around, I think well, I should not say it, but it's way less than millions of TVL like funds there, and it's more of a small fund. And sometimes like, but I think the most meaningful things we have done is that we found like hackers, like true hackers that I mentioned before, that they have their hacking helper contract trying to attacking the victim, but like we front run before that. Wasting their resources. Well, if there's a limit. Like for us, I think we stop at 200 can runs per contract. But yeah, that's a good try. But on Ethereum, like back in last year, deploying a contract can be expensive. Like you spend dollars or tens of dollars to deploy one. Any more questions? Anything related to the lecture, or can you share the link? Yeah, let me share again. Did someone raise hand? Yeah, and how's the lecture about fuzzing? Did you guys find it like interesting or hard or easy to understand? I'm also like open to those questions too, if you want.
So did you ask about the fuzzing lecture with Aki? I missed this part.
Oh.
Yeah, it was quite a, I would say, more introductory lecture, but yeah, they did show some examples of how to run Trident, the setup and stuff like that. But we're gonna release this lecture hopefully by the end of the day today. So we're just fixing the something on post production, but yeah, should be live today. Yeah, if you want to check it out, I can also drop the slides and yeah.
So I feel like as a security researcher, I feel like on Solana, because people are, you know, writing code with Rust, the only thing they care about, like for dev, you only need to focus on the access control. Like you have Anchor, right? And don't touch Pinocchio until you fully understand how the checks work, how the Anchor macro like expansion works. As long as you use Anchor, you only need to check like access control, and that already gives hacker like a big problem. Like all the hacks I saw on Solana, it's because of access control. There's no like sophisticated attacks on Solana. It's just access control. They forget to add some standard check or authority check. If you are a developer, keep that in mind. And if you are a security researcher or bug bounty hunter or auditor, also focus on that only because most time you don't. There's no that many bugs on Solana written Anchor written programs. It looks the tooling EVM is way mature than in Solana. That's true. That's true because like EVM like is years ahead of Solana, right? And people just started to transition into Solana since last year. And to be honest, like dev experience on Solana is not as good as on Ethereum. And I feel that this Rackov bootcamp is already it's really good. I read about the fundamentals, the first few lectures where you get taught about the memory layout and how like Rust code are translated or compiled into low-level memory operations, and that's all you need to know. If you want to like after you understand how the memory works there, you are safe to use. You're safe to write Solana native program or Pinocchio based ones. But like before that, you like using Anchor is already prevent you from a lot of security pitfalls there. But like Anchor is too, I know it's like too heavy and not optimized. But so far, like Anchor, it's like transaction fee on Solana is cheap, right? So people really don't like give a shit about like how much they spent on the CUs there so far. But I think people will like optimize their code to Pinocchio finally. Yeah.
Yeah, thanks for the feedback on the first few lectures. I think that was the whole thinking behind like a lot of people are hopefully will be starting playing around with Pinocchio and just especially for security researchers, when you try to understand the design of the program, the importance of actually understanding the low-level design of the language and how it all works. I think that's one of the key aspects of learning, and not just learning tools and learning like Anchor and stuff like that. So yeah, definitely, yeah, appreciate the feedback. I'll pass it on to Daniel, who's the tutor on the first module, and yeah, I think we can probably wrap this lecture up at this point if no more questions coming. Yeah, you can always find Chi either on Twitter or in our Slack. Just feel free to tag him and ask any questions. But yeah, we'll compile a list of all the resources that we discussed today. And thank you so much again for coming and doing this. I know it's kind of early morning for you, but yeah, appreciate joining.
Yeah, thank you.
Cool. I'll see you all in Slack. Bye bye, guys.
Bye.